Hello there, Algebra 2 students. This video is going to go through our notes over simplifying nth roots. So you can see as the top, the title for today is Simplifying Nth Roots. So what we're going to talk about in this video is how do we simplify not just square roots, but third roots and fourth roots and fifth roots and so on and so forth. So a big piece of simplifying these roots is, first of all, knowing what our perfect squares are and perfect cubes are. So you can see here in red, kind of the second thing there says perfect roots. So I'm going to go through here, and you'll notice on the far left column, it has your kind of like your n value. So we have 2 through 10, and then in the next column it says n squared. So we're going to want to know, okay, what is in this first row, first column, what is 2 squared? Well, 2 squared is 4, and then 3 squared is 9, and then we can keep going, simplifying or writing out each of the perfect squares. So if I keep going here, now we have all of our perfect squares. And we're going to do this for not only the perfect squares, but now if you look in the next column where it says n cubed at the top, we're going to do this for all our perfect cubes. So we're going to say, okay, well, 2 cubed, that's 8, and then 3 cubed, that's 27, and then we're going to keep going. So you can use a calculator, and you can come up with many of these on your calculator, but having this list or this chart of our perfect squares and our perfect cubes is going to help us simplify all of these nth roots. So whether it's a square root or a cube root. So I'm going to keep going in the chart here really quick. I would use my calculator. So 2 to the 4th is 16. And then if I do my fifth root, or sorry, my fifth powers, and then my sixth powers, and then my seventh powers, all right, so there's our chart completely filled out with all of our kind of like perfect powers. So we've got our squares, our cubes, our fourths, our fifths, so on and so forth. So if I kind of scroll down here, we're going to use this chart, and you'll notice I have there as my first example, it says simplify, and then I have a part A, a part B, and a part C. And in each one, we're taking a root of 128. In A, it's the square root, in B, it's the cube root, and in C, it's the fourth root. So if I start here, I'm going to change my colors to blue, and we're going to say, okay, we've done something like this before. If I want to know the square root of 128, then I'm going to look up here in my table, and I'm going to say, okay, what is a perfect square that divides 128? Usually it's easier to start with your biggest numbers, so I might start with 100 and say, okay, well, does 100 divide 128? Well, the answer is no, so probably not a good idea to use 100, and we can go through here. 81's probably not going to work. But when we get to 64, we could say, okay, well, look, this is like the square root of 64 times 2, and then we could say, okay, if we were to break that up, we'd have here the square root of 64 times the square root of 2. Excuse me. And then if I look at my chart, I could say, well, 64 was what number squared? Well, it was 8. So this would simplify to 8 square roots of 2. So there is my final answer. That is the simplified answer for the square root of 128. So we're going to do very similar kind of steps. So like we did in part A there for part B and C. Now, when we look at part B, it says the cube root of 128. So if we're going to take the cube root, instead of in our table looking at what I kind of circled there or kind of boxed in blue, we're going to say we need to look at our perfect cubes. So I'm going to look at this kind of column here that I'm highlighting in my kind of orange. And I'm going to say, okay, now I need a perfect cube that divides 128. Well, I'm probably not going to use any number bigger than 128. So if I go through here, well, 64 happens to be also a perfect cube, so we could say, okay, well, look, this is like the cube root of 64 times 2. And then we could say, okay, this is like the cube root of 64 times the cube root of 2. And I'm going to look at my table and I'm going to say, okay, well, 64 was what number cubed? Well, it was 4. So the cube root of 128 would simplify to 4, because that's what the cube root of 64 simplifies, times the cube root of 2. My 3 is kind of hard to read there, but notice how we have the 3 kind of inside the root check mark there, the little like root symbol. So that 3 signifies that it's the cube root. All right, so if we go ahead and we try another one here, let me grab a different color. So maybe if I use purple here for letter C, we're going to do the same thing, but now we're going to take a fourth root. So if it's a fourth root, we're going to need to look at our perfect fourth powers. And again, we're going to need to figure out, okay, what's a perfect fourth power that's going to divide 128? So I'm not going to use anything bigger than 128. I don't think 81 divides 128 evenly, meaning it's going to give me some kind of decimal, so I'm not going to use that. But we do notice that, okay, 16 does, right? So we could say, well, look, this is like the fourth root of 16 times 8. And then I can go ahead and say, okay, well, 16 was what number to the fourth power? Well, if we look over there, it's 2, so this would be like 2 fourth roots of 8. Now, some of you might look at that and say, well, look, let's simplify that a little bit more, right? We got the fourth root of 8. Well, but remember, since it's the fourth root, I got to look for a number inside that column into the fourth, and there's no number there that is less than 8, so there's definitely not going to be a number that is going to divide 8 evenly. All right, so there are 3 different examples. I forgot to circle our B. So there are 3 different examples of how we might simplify a square root or a cube root or a fourth root of just a number. All right, so I'm going to go ahead and scroll on here to kind of an on your own example. So if you want to try this one on your own, now would be a good time to pause the video, try it on a piece of scrap paper, and then come back. So we're going to go ahead and we're going to go through this one together. So if we have here the fifth root of 3072, then if I kind of slide back here to my table, since we're looking at fifth roots, we're going to need to look at our perfect fifth powers, so our n to the fifth kind of column there. And I'm going to say, okay, well, what's a number that divides that 3072 evenly? I might try 1024, and I could say, okay, in my calculator, what is 3072 divided by 1024? And if I do that in my calculator, I believe I get 3. So if we come back here, we could say, okay, well, look, this is like the fifth root of 1024 times 3. We saw that 1024, that was 4 to the fifth, so that means that we're going to have a 4 outside, and then we'll have fifth root, and then our 3 is left underneath the fifth root. We can't simplify that anymore. So there would be just another example, in this case, fifth root, of taking an nth root of just a number. All right, so we'll come to variables here in a minute, but so far we're just talking about numbers. All right. Second example here says approximate the seventh root of 500 with your calculator. So not all perfect roots we're going to get like nice simplified whole numbers. There could be decimals. So really quick, there are a couple different ways you could do this problem. So first, if we wanted to come up with the seventh root of 500, one way we could do that is we could use our calculator, and we could go to the math menu. So there should be a a button up in the left-hand corner that says math. And then in that menu, you're going to look for the little thing that looks like the X root. All right. And if you go ahead and you type that in, you should be able to come up with the seventh root of 500. Now, another way we could do this is if you happen to look at our last video when we talked about writing roots as rational exponents, we could write this as, instead of a root, we could write it as an exponent. And we could say, okay, well, look, the number underneath my root happens to be 500, so this would be the same thing as 500 to the And then if I think about here, what is my power of that? Well, it's just 500, so that would be like 500 to the first. So if we think about writing this fractional exponent, it would be to the power 1 over, and then whatever our root is, in this case, we're taking the 7th root. So this 7th root of 500 is the same thing as 500 to the 1/7 power. And if you were to type that into your calculator would give you a decimal, and it would say, well, hey, this is approximately 2.429. So there's just another way in your calculator you can come up with an approximation for a root other than just a square root, right? We have that square root button, but there are also other roots. Now, hopefully that we have a good grasp on taking the nth root of numbers, we're going to start mixing in some variables. So I have here 4 examples. There's an A, there's a B, there's a C, and there's a D. We're going to start here with A, and what we're going to do is, before we start kind of like trying to simplify any of this stuff, I'm going to rewrite it. So if we look at A, it says the cube root of 27 x to the 5th y squared z to the 6th. So first thing I'm going to do is I'm going to say, okay, if we were to rewrite this, this would be like the cube root of, and then in here we'd have 27 times. Now, x to the 5th is like 5 x's. So that's like an x times an x times an x times an x. And then here, if we take our y squared, that's like times a y times a y. And then if we take our z to the 6, I need here 6 z's. I'm going to run out of room almost. 6 z's there that we're going to go ahead and we're going to multiply. So if we think about this, I'm going to start with the number piece like what we did kind of in the last couple examples. And if we want to know the cube root of 27, well, then we need a perfect cube that divides 27. So if you were to go back, if I slide back here really quick, I know it's hard to tell, but our perfect cubes is kind of that yellow column. And I'm going to look for, okay, what's a number that divides 27? Well, it just so happens that 27 is a perfect cube. So we could say, okay, well, look, the cube root of 27, well, that's just 3, right? So we can simplify that. The cube root of 27 is just 3. Now, if we go ahead and we talk about our variables, since it's the cube root, what we're really doing is we're looking for groups of 3. So if I look at my x's, I'd say, okay, well, look, just looking at my x's, I have here one group of 3, and then I kind of have like 2 left over. If I do the same here, let me choose a different color. With my y's, I'd say, okay, well, I only have 2 y's. I don't have any groups of 3, but I have 2 y's kind of left over. And then if I choose kind of like a last color here, if I look at my z's, I'd say, okay, well, look, I have 2 groups of z's, right? 2 groups of 3, and I have none left over. So if we take what we've done right here, I'm going to start with a number, and I'm going to say, okay, if we were to simplify this, this is all going to simplify. Well, the 3 here was the cube root of 27, so that's going to come out in front of our cube root. I was able to get here one group of x's. So if I kind of there look at my yellow, so my x is going to come out in front because I had one group of them. I had 2 groups of my z's, so I'm going to bring 2 z's out. And rather than writing a z times a z, I'm going to say, okay, well, look, that's a z squared. And then underneath the cube root is going to be all of our leftovers. Well, the cube root of 27, well, we knew the cube root was just 3, so there were no leftovers. If we look here at our x's, right, we had one group of 3, we had 2 left over. So instead of writing x times x, we're going to say, well, look, we have an x squared left over inside the cube root. If I look here at my y's, I had 2 y's that were kind of left over. I wasn't able to get any groups of 3. So rather than writing a y times a y, I'm going to write a y squared. If I look at my z's, we had 2 groups of 3, but we didn't have any left over. So that means there's going to be nothing left over for our z's underneath our cube root. So our final answer for simplifying this in part A is just right there. So you're really, since we're taking the cube root, when you think about the variables, then you're looking for groups of 3. So how many groups of 3? For each group of 3, I can bring that variable out in front of our root. And then for our leftovers, that's going to stay underneath, in this case, our cube root. All right. So we're going to do one more example, very similar to that first one in A. So if you look at B, instead of the cube root, it now says the fifth root. So we're going to say, okay, we need to take the fifth root of 24, A to the sixth, B to the 21st, C to the fourth. So again, I'm going to kind of rewrite this similar to what we did in A, but since we know that it's the fifth root, we know we're going to be looking for groups of 5. So if I start here with the fifth root, and I'm going to start here with the number, and I'm going to say, okay, 64. So you can go back to that table we kind of started our notes with, and I can look for what's a perfect fifth power that divides 64. Well, one that I noticed right off the bat is I noticed, well, 32 was in our list, and 32 times 2 gives me 64. So I'm going to leave that there for right now. That's kind of like our number piece. And then we're going to go through and we're going to do our variables just like we did. Now, instead of writing out A times A times A 6 times and B times B times B 21 times, and the same for C's, since I know it's the fifth root, I'm looking for groups of 5. So I'm going to say, okay, starting here with my A's, if I have A to the 6th, I know I'm going to be able to get one group of A to the 5th. And then I'm going to have one A kind of left over. So I'm just going to rewrite it like that. I'm not going to write out all 6 A's. And then if we do the same here for our B's, well, if I think about how many groups of 5, I'm going to get one group of 5. There's 5 of my B's. Then I'm going to get another group of 5, so that's 10 of my B's. Then I'm going to get another group of 5, so that's 15 of my B's. And then I'm going to get another group of 5, that's 20. And then I'm going to have one B kind of like left over. All right, so then I'm going to do the exact same thing here for my C's. And I'm going to say, okay, well, I got a C to the 4th. How many groups of 5 can I get? And then how many leftovers? Well, if I just have a C to the 4th, I can't get any groups of 5, but I'm going to have 4 left over. So I'm going to write there kind of C to the 4th. Then what we're going to go through here is we're going to just simplify kind of each piece and part of this. So if I think about this piece here, I'm going to do the number first kind of over here. And I'd say, well, look, the fifth root of 32, well, what number to the fifth power equals 32? Well, that was 2. So a 2 is going to come outside the fifth root because we know the fifth root of 32. And then we have this leftover piece here, this 2. So that's going to mean that underneath the fifth root, there's going to be a 2 kind of left over. So just talking about the numbers. Now, let's talk about the variables. So I'm going to come write our final answer down here. We have that 2 out front. How many groups of 5 are we able to get out of our A's? We're able to get out 1, so I'm going to put a A out front. Then we'll come back and we'll talk about our leftovers. So for right now, we're going to leave that there. But then if I look at my B's, I have 1, 2, 3, 4 groups of 5. So rather than writing B times B times B 4 times, we're going to say, okay, a B to the 4th on the outside because we had 4 groups of 5. We had 1 leftover B, and then we just had some leftover C's. So our leftovers are going to stay underneath our fifth root. So first from our number, we had this 2. Then from our A's, we had 1A. Then from our B's, we had 1B. And then we had our 4 C's. So there is our final answer for letter B, for simplifying that fifth root. So we have the 2 out front, we have an A out front, we have a B to the 4th out front, and then we have times the fifth root, and then what stays underneath there is always our leftovers. All right. So A and B are going to be very similar to what you see kind of in your homework or in ALEKS. If we look at letter C and letter D, these are kind of special cases. So if I look really quickly at letter C, it says take the square root of x squared plus 6x plus 9. Now, a hesitation of mine and something that I see several students do is they say, okay, well, Mr. Jordan, why don't we go ahead and say square root of x squared plus square root of 6x plus square root of 9. This is a big no-no. You cannot simplify a square root by breaking it up. So you cannot go through and just take the square root of bits and pieces. If it's a square root of a whole expression, that whole expression has to stay underneath there. So what that means is we need another method or another way to deal with this expression, x squared plus 6x plus 9. Now, something we've done all year, and we did it a ton in second quarter, and we did it a ton in third quarter, is we talked about factoring. So why don't we try factoring with this? So if I go ahead and I set up my two sets of parentheses, well, we know x times x is going to give us x squared. And then we can say, okay, well, what two numbers are going to add to give us 6x and multiply to give us 9? Well, hopefully a lot of us come up here with 3 and 3, so we'd have x plus 3 times an x plus 3. And hopefully even we would notice, well, look, if I have an x plus 3 times an x plus 3, that's the same thing as x plus 3 squared. So we can rewrite this whole thing as now the square root of x plus 3 quantity squared. And like we've talked about many times so far this year, is if we have the square root of something squared, where the whole quantity is squared. Notice I can't do what I did there earlier in red, where I break up the pieces and parts. But if I have the square root of a whole quantity that's squared, remember the square root and the square kind of like undo each other. They get rid of one another. So that leaves us with a final answer of just x plus 3. So we could say, okay, there is my final answer. All right. So don't forget factoring as one of your methods or strategies in order to solve. And last but not least, if we look at example D, it says the square root of x squared plus 4. So if you have the square root of x squared plus 4, remember, I cannot split up that square root. So we'd say, okay, well, how about if we take this expression under here, and like we did in C, could we factor x squared plus 4? Well, it is two perfect squares, but notice it's not a difference of two, it's a sum. So here, if we can't factor it and we can't split it up, right, then there's no way we can simplify it. So we would just write here, does not, so let me write this here, does not simplify. There is no way for me to go through here and simplify the square root. All right, so there are kind of 4 examples. Probably A and B are the two that will be most common as you go through ALEKS or you look in your homework. Hopefully this helped. If you have questions, make sure you ask. That's it. I will talk to you.